Welcome! In today's problem walkthrough, we'll explore problem number 833, find and replace in string. This problem will challenge us to manipulate strings efficiently while maintaining their structure. Let's dive in. In this problem, we are tasked with modifying a string based on a series of replacement instructions. Specifically, you're given a string S along with 3 additional inputs, an array indices, an array sources, and an array targets. The goal is to replace certain substrings of S with corresponding values from targets, but only if those substrings match the strings and sources at the specified positions in indices. The rules are straightforward. First, if the substring at indices, I, matches the value in sources, I, then it should be replaced with targets, I. However, if there is no match, the replacement for that index is skipped. Another important aspect is that all of the replacements need to happen simultaneously. This means no replacement can interfere with or overlap another, ensuring that the result is consistent regardless of the order in which the replacements are processed. The final output is the modified string after applying these rules. The output for this problem is a single string, which represents the result of performing all valid replacements on the input string S. To help clarify how this works, let's look at an example. Say the input string S is ABCD, with indices as 0, 2, sources as A, CD, and targets as E, FFFF. The first replacement occurs at index 0, where the substring A matches sources, 0. Here, A is replaced with targets, 0, which is E. Next, at index 2, the substring CD matches sources, 1, so it is replaced with targets, 1, which is FFFF. After applying both replacements simultaneously, the resulting string becomes EPF. This demonstrates how matching substrings are replaced while preserving the integrity of the process. Now, let's examine another example to understand what happens when some replacements are skipped. Consider the input S as ABCD, with indices as 0, 2, sources as AB, EC, and targets as E, FFFF. For the first replacement, the substring starting at index 0 is AB, which matches sources, 0. This allows us to replace AB with targets, 0, which is EE. However, for the second replacement at index 2, the substring is CD, which does not match sources, 1. Since there is no match, this replacement is skipped entirely. The resulting string after these operations is EKed. This example highlights that only valid replacements are performed, and mismatches are ignored. Let's look at one final example where no replacements are valid. Suppose the input string S is XYZ, with indices as 0, 1, 2, sources as B, C, and targets as D, E, F. In this case, none of the substrings starting at the specified indices match any of the values in sources. For instance, at index 0, the substring is X, which doesn't match sources, 0, A. Similarly, at indices 1 and 2, the substrings Y and Z do not match their respective sources values. Since no replacements are valid, the original string remains unchanged, and the output is simply XYZ. This example underscores the importance of matching substrings exactly before performing any replacements. To wrap up, there are a few constraints and edge cases to keep in mind. The string S has a maximum length of 1000, while indices can have up to 100 elements. Each value in indices points to a distinct position in S, and the lengths of sources and targets are always equal. Edge cases include scenarios where none of the replacements are valid, in which the input string is returned as is. Another important point is that replacements are guaranteed to occur simultaneously, so there's no risk of overlaps between them. This ensures that the problem remains deterministic and avoids ambiguity. By carefully applying these rules, you can handle all valid replacements and produce the correct result efficiently. To begin, let's consider the brute force approach for solving this problem. The idea here is straightforward. We iterate through the indices array and, for each position, check if the substring in S matches the corresponding sources, I. If a match is found, we replace that substring with targets, I, directly. The process involves sequentially updating the string, which means we must carefully track changes to avoid issues with subsequent replacements. However, this approach has significant drawbacks. The time complexity is O, n asterisk m, where n is the length of the indices array and m is the average length of the substrings and sources. This inefficiency arises because modifying the string repeatedly during iteration is computationally expensive. Additionally, it can lead to errors if we don't carefully account for how changes in the string affect future operations. While conceptually simple, this method is both cumbersome and error-prone. Now, let's explore a more efficient solution, the optimized approach. The key idea here is to avoid the pitfalls of sequential modifications by using a delayed replacement strategy. To achieve this, we first sort the indices array in descending order. This allows us to make replacements from right to left, ensuring that earlier modifications do not interfere with subsequent ones. The steps are as follows: we zip the indices, sources, and targets into a list of tuples, then sort these tuples by the indices in descending order. For each tuple, we check if the substring in S starting at the given index matches the corresponding source. If it does, we replace it with the target. This approach is highly efficient, with a time complexity of O, n plus m, where n is the length of the string and m is the size of the indices array. The additional space required is O, m, for storing the sorted tuples. By avoiding intermediate string adjustments and ensuring replacements are independent, this method guarantees correctness and improves efficiency. Based on these considerations, we chose the optimized approach as the most suitable strategy. Its combination of clarity, correctness, and efficiency makes it ideal for this problem. Sorting the indices in descending order ensures that replacements are non-overlapping and independent, eliminating the risk of interference. Additionally, the one-pass replacement process minimizes complexity while maintaining accuracy. This strategy strikes a balance between performance and simplicity, addressing the shortcomings of the brute force approach and providing a robust solution to the problem. In this problem, we are given a string S and 3 arrays, indices, sources, and targets. The task is to replace specific substrings in S based on the data from these arrays. Each indices, I, tells us the starting index of a substring in S. If the substring starting at that index matches sources, I, we replace it with targets, I. If there is no match, the string is left unchanged at that position. A brute force approach to solving this problem involves iterating through each index and indices and applying replacements as needed. To begin, we validate the inputs by ensuring that the lengths of indices, sources, and targets are equal and that all indices are within the bounds of the string S. Once the inputs are confirmed to be valid, we initialize a result holder by converting the string S to a list of characters. This step is crucial because strings are immutable, and modifying a list is far more efficient when making multiple updates during the replacement process. Next, we proceed to iterate over each index in the indices array. For each I, we extract the substring from S starting at indices, I, with a length equal to the length of sources, I. We then check if this extracted substring matches sources, I. If it does, we perform the replacement in the result holder, which involves removing the original substring and inserting the corresponding targets, I. This can be achieved using slicing or directly updating the character list. If there is no match, we simply move on to the next index without making any changes. Once all replacements are processed, we reconstruct the final string by converting the modified character list back into a string. Finally, we return this updated string as the output of the algorithm. There are a few key insights that simplify the problem. First, replacements are non-overlapping, meaning they do not interfere with one another. This allows us to process each replacement independently without worrying about cascading changes. Second, the order in which replacements are performed is critical. Since indices are processed sequentially in the given order, sorting the indices array beforehand could lead to incorrect results. Additionally, certain edge cases must be handled carefully. If an indices, I, points to a substring that exceeds the bounds of S, the replacement should be skipped. Similarly, if sources, I, is an empty string, we ignore that replacement. If targets, I, is empty, it is treated as removing the substring. To handle these replacements efficiently, we use a character list for intermediate updates, as it allows in-place modifications. The input array's indices, sources, and targets are used directly for sequential processing. To optimize the solution, we can introduce a few enhancements. One approach is to skip invalid replacements early by checking if indices, I, and the length of sources, I, are valid for the string S before performing any substring extraction. Another optimization is to group indices by their starting positions to minimize redundant checks or processing. Analyzing the complexity, the time complexity of the algorithm is O, n asterisk m, where n is the length of the indices array, and m is the average length of sources, I. For each index, substring extraction and replacement take O, m, time. The space complexity is O, k, where k is the length of the string s, because we use a character list to hold the intermediate result during replacements. These optimizations and complexity considerations ensure that the solution is both correct and efficient. Let's walk through an example to see the algorithm in action. Suppose we are given the string s equals abcdxyz, with indices equals 0, 4, sources equals ab, xy, and targets equals 12, 78. First, we convert the string s into a character list, a, b, c, d, x, y, z. Now, we process the first index, indices, 0, equals 0. We extract the substring s, 0:2, equals ab, which matches sources, 0. We then replace ab with 12, resulting in the character list, 1, 2, c, d, x, y, z. Next, we process the second index, indices, 1, equals 4. The substring s, for :6, equals xy matches sources, 1, so we replace xy with 78. The updated character list becomes 1, 2, c, d, 7, 8, z. Finally, we convert the character list back into a string, yielding the result, 12cd78z. This string is returned as the final output of the algorithm. This solution defines a function findReplace string inside the solution class, which takes the string s and three lists, indices, sources, and targets as input. The goal is to replace specific substrings in s based on the given indices, sources, and targets. The function first creates a list of tuples, each containing an index, a source substring, and a target substring. This list is sorted in reverse order based on the indices. Sorting in reverse ensures that performing replacements does not affect the positions of the remaining indices in the string. For example, modifying earlier parts of the string first might shift later indices, causing incorrect replacements. Next, the function iterates over the sorted replacement list. For each tuple, index, source, target, it checks if the substring of s starting at index matches source. If it matches, the function performs the replacement using string slicing. The string s is updated by concatenating the portion before index, the target, and the portion after the replaced substring. Finally, the modified string s is returned as the result. This implementation handles all edge cases, including non-matching substrings, skips replacement at that index, overlapping indices, avoided by reverse sorting, empty sources or targets. The time complexity is O, n plus m asterisk k, where n is the length of s, m is the number of replacements, and k is the average length of the substrings. Sorting the replacements takes O, m log m. The space complexity is O, m, for storing the replacement tuples. Here, we start by importing the necessary packages and defining our solution class with the method findReplaceString. The goal of this method is to perform multiple find and replace operations on the input string s. To begin, we combine the indices, sources, and targets into a list of arrays where each array contains the index and its corresponding position in the sources and targets arrays. This setup allows us to keep track of which replacement corresponds to which index. Next, we sort this list in descending order based on the indices. Sorting in reverse order ensures that we process replacements from right to left, which prevents earlier replacements from altering the string in a way that would interfere with later ones. After sorting, we move on to the main logic where we iterate through the list and check if the substring at the given index matches the corresponding source string. If it does, we use the string builder's replace method to substitute the matching substring with the target string. Finally, after completing all the replacements, we return the modified string by converting the string builder back to a string using its toString method. This approach is efficient because string builder allows us to make in-place modifications, avoiding the overhead of creating multiple intermediate strings. The method ensures that all replacements are applied correctly and in the desired order, resulting in the final transformed string. This completes the implementation of the find and replace algorithm in Java. To solve this problem, we start by combining the given indices, sources, and targets into tuples. Here, the input string is ABCD, the indices are 0, 2, the sources are A, C, D, and the targets are E, F, 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 F. Combining these gives us the tuples 0, A, E, 2, C, D, F, 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 F. To handle replacements efficiently, we sort these tuples by their indices in reverse order, resulting in 2, C, D, F, 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 0, A, E. This ensures that processing the replacements from the highest index first avoids issues with shifting indices. Now, we begin processing the first tuple, 2, CD, FFFF. The substring CD from index 2 to 4 matches the source CD. So, we replace it with the target FFFF, updating the string to AF. Next, we process the tuple, 0, A, E. The substring A from index 0 to 1 matches the source A. Replacing it with EE transforms the string to EBF. The final output after both replacements is EBF. In this example, we are testing a case where no replacements are made because the sources do not match any parts of the string. The input string is ABCD, the indices are 0, 2, the sources are X, Y, Z, and the targets are E, F, 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 F. Combining these into tuples gives 0, X, E, 2, Y, F, 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 which we sort by indices in reverse order, resulting in 2, Y, F, 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 0, X, E. Starting with the tuple 2, Y, Z, F, 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 we check if the substring CD from index 2 to 4 matches the source YZ. It does not, so no replacement is made. Moving to the tuple 0, X, E, we check if the substring A from index 0 to 1 matches the source X. Again, there's no match, so no replacement occurs. Since neither source matches any part of the string, the final output remains unchanged as ABCD. Here, we examine a case with overlapping indices. The input string is ABCD, the indices are 1, 0, the sources are BC, A, and the targets are XX, YY. Combining the indices, sources, and targets into tuples gives 1, BC, XX, 0, A, YY. Sorting by indices in reverse order keeps the order the same, 1, BC, XX, 0, A, YY. Starting with the tuple 1, BC, XX, we check if the substring BC from index 1 to 3 matches the source BC. It does, so we replace it with XX, updating the string to AXTA. Next, we consider the tuple 0, A, YY. The substring A from index 0 to 1 matches the source, so we prepare to replace it with YY. Replacing the substring A with YY involves updating the string as follows: S equals S, shocked, plus YY plus S, 1, smiley face, which results in YXT. The final output after processing both replacements is YXT. Key points to note from this example include the importance of sorting the replacements in reverse order to handle overlapping indices without causing unintended shifts. Additionally, each replacement is only applied if the substring matches the source exactly, ensuring the integrity of the operation. By following this method, we can handle string replacements efficiently and correctly, even in cases with overlapping indices or mismatches. To analyze the time complexity of the provided solution, we can break it into two main components. First, we have the sorting of the replacements list. The zip operation combines the indices, sources, and targets into a list of tuples, and this step takes O, K, where K is the total number of replacements. The sorting of this list, performed in reverse order based on the indices, takes O, K asterisk log, K. Next, we process the replacements. The for loop iterates over the sorted list, and during each iteration, it performs a substring extraction. This operation depends on the length of the source string being replaced and contributes O, len, source, per iteration, which accumulates across all sources to O, sum, len, source underscore I. Additionally, string slicing and concatenation are performed to create a new string. Since this involves copying the entire string for each replacement, it contributes O, K asterisk lens, in total. These steps together form the basis for the overall time complexity. Now, combining the components discussed earlier, we have the sorting step with a complexity of O, K asterisk log, K, and the replacement processing step, which has a complexity of O, sum, len, source underscore I, plus O, K asterisk lens. In the worst case, if the length of all sources is proportional to the length of the string S, this simplifies to O, K asterisk, lens plus log, K. Moving on to space complexity, there are three key considerations. First, the zip operation creates a list of tuples, which takes O, K, additional space. Second, the sorting process incurs extra overhead, also requiring O-K space. These are the primary contributors to the space requirements so far. Additionally, we must account for the space used during string manipulation. Every time we perform string slicing and concatenation, a new string is created. In the worst case, the total memory used for these intermediate strings is proportional to O-lens. Combining these factors, the overall space complexity of the solution is O-K plus lens. To put this into perspective, let's compare it to a naive approach. A brute force method might involve directly iterating over the string and checking for matches for each replacement without sorting. This could lead to overlapping replacements and multiple passes over the string, resulting in a time complexity of O-lens *k. The provided solution avoids this inefficiency by sorting the replacements in reverse order, ensuring that earlier indices remain unaffected by subsequent modifications. This makes the optimized approach much more efficient under the given constraints. Now, we can analyze the best, average, and worst cases for this solution. In the best case, none of the replacements are valid, meaning no modifications to the string are needed. In this scenario, sorting dominates the time complexity at O-K log k. In the average case, some replacements are valid, and the complexity depends on the number of replacements and the string length, generally expressed as O-K lens plus log k. In the worst case, all replacements are valid, and each replacement involves handling large substrings, resulting in the same overall complexity of O-K lens plus log k. In conclusion, the provided solution strikes a balance between processing efficiency and clarity by leveraging sorting and reverse processing to handle replacements without interference. While string slicing and concatenation still incur costs, these are inherent to the problem structure. The algorithm efficiently handles the trade-offs, ensuring that the time complexity is dominated by the number and length of replacements, and the space complexity remains linear with respect to the input size. When solving this problem, there are several common mistakes to watch out for. First, it's crucial to ensure that the substring from the original string S starting at indices I matches sources I. If this validation step is skipped, you might end up performing replacements incorrectly or skipping valid ones. Another issue arises with overlapping replacements. If you modify the string S in place, replacements at nearby indices can interfere with each other, leading to unintended results. To avoid this, a good strategy is to process the replacements in reverse order of indices. Additionally, don't assume that the indices array is sorted. If it's not, you'll need to sort it and rearrange sources and targets accordingly to maintain alignment. Since strings are immutable in many languages, directly modifying S can be error-prone and inefficient. Instead, it's better to construct the result string incrementally. Finally, always account for edge cases, such as empty inputs or situations where an index is out of bounds, and ensure your solution gracefully handles these scenarios. This problem has some interesting insights that can help you approach it more effectively. One way to think about it is to see the indices as starting points of intervals, similar to interval problems. This perspective helps ensure that transformations don't overlap or interfere with each other. Sorting the indices and processing them in reverse order is often the optimal strategy, as it prevents earlier replacements from disrupting later ones. Another consideration is the trade-off between space and time. While building the result string incrementally minimizes memory usage, using additional data structures, such as a mapping of indices to their corresponding replacements, can make your code clearer and reduce the likelihood of errors. It's also essential to test your solution thoroughly. Edge cases, like partial matches or unsorted and overlapping indices, can reveal potential flaws in your approach. Additionally, this problem shares similarities with other challenges, such as adding bold tags to strings or working with interval intersections, so understanding these related problems can give you a broader toolkit for solving similar tasks. There are also alternative approaches you can explore to solve this problem. One such method is the hash map approach, where you create a dictionary that maps each indices, I, to its respective sources, I, and targets, I. This allows you to validate matches and construct the result string without modifying S directly, though it requires additional space. Another option is the two-pointer technique, where one pointer iterates through the string S while the other tracks the indices. This approach minimizes extra space but can be tricky to implement correctly when handling replacements. Each method comes with its own trade-offs. A brute force approach, though easy to implement, can be inefficient, especially if the length of sources, I, is large. On the other hand, optimized sorting reduces complexity by sorting indices and processing replacements efficiently, but it requires extra pre-processing. Finally, while constructing the result string incrementally is space efficient, it can be more challenging to debug compared to hash map-based solutions. The choice of approach often depends on the constraints and priorities of your specific implementation. Great work! Today, we tackled a challenging yet rewarding problem on string manipulation. Remember to practice similar problems to reinforce your skills. Thank you for watching, and I'll see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!